You might recall working with sequences in your Calculus 2 course. Most students learn just enough to get through and then forget it all after the exam. But it turns out that sequences are one of the key concepts we need to understand in order to be successful in real analysis. So we will take the time to rebuild the intellectual foundations of sequences and convergence. The common sense idea of a sequence is that it is an infinitely long list of numbers in a specific order. However, we need to formalize this idea if we're going to be able to prove anything about sequences. First, we will introduce a general notation for sequences. At this point, we can see that we can write down a function to represent this sequence. This observation leads us to the following definition. Definition: a sequence is a function whose domain is a set of the form set of all integers n such that n is greater than or equal to m. This seems a bit strange at first, but for some sequence it makes sense to start at places other than 1. We will use a special notation to denote the set of integers that are greater than or equal to m. Recall that a function is just some rule for associating elements of one set with elements of another. Since this is a course in real analysis, the codomain is going to be the set of real numbers. When working with sequences, it is easy to get confused because we talk about many parts of the sequence using notation that looks very similar. When we talk about a sequence, it will be denoted using parentheses around either a list or a generic symbol that represents a formula. Sometimes we will be explicit about the domain, but most of the time this information will be inferred from the context. It's very important that when we're talking about a sequence that we're taking the order of the elements into consideration. If we wanted to consider the set of points that corresponds to a sequence, we would use set brackets and the standard set notation. In the context of sequences, we often don't explicitly indicate that the index is restricted to integers. The important distinction is that when we're talking about sets, we do not care about the order in which the terms appear. If neither parentheses nor set brackets are present, then we are referring to specific individual terms in the sequence. An interesting feature of sequences is that sometimes the values get closer and closer to some specific number. For example, the terms in the sequence 1 over n are very close to 0 when n is very large. This is known as convergence. But what do we mean by the words very close and very large? This will be easier to understand after we look at the formal definition. Definition: a sequence S sub n of real numbers is said to converge to the real number s, provided that for each epsilon greater than 0, there exists a number capital N such that little n greater than capital N implies that the absolute value of s sub little n minus s is less than epsilon. In this definition, epsilon is what we use for very close, and capital N is what we use for very large. Basically, this says that no matter what tiny distance you pick, if we go far enough into the sequence, then every single value beyond that point is closer than that to the limit. We will break this definition down piece by piece. Let's look at a picture of the generic sequence S sub n that's converging to S. At first, the sequence can be very erratic, but for it to converge, it means that eventually it settles down and all the values become very close to S. The value epsilon creates a narrow band around S. The task is to find a number capital N so that everything beyond capital N is within that band. Notice that if we make epsilon smaller, we have to push n further out. The claim of convergence is that no matter how small we make epsilon, we will always be able to find an n far enough out so that all the terms in the sequence fall within that band. In class, we will work with numerical examples to show the interplay between epsilon and n to build a deeper understanding of the concept of convergence.